Every second of every day, the sun bombards our planet with massive amounts of raw energy. This raw energy travels across the vacuum of space in tiny, incredibly fast packets of light called photons. But most of that energy goes completely to waste. When those photons strike standard surfaces down here on Earth, like a concrete sidewalk or an asphalt driveway, they simply bounce off, dispersing into the air as useless ambient heat. Capturing that chaotic radiation before it dissipates is a massive engineering challenge. To actually harvest it, we have to cross a very specific technological threshold. That threshold is the modern solar panel. Unlike the pavement, it is precisely engineered to absorb those incoming photons rather than reflect them. That absorption dictates the design. The top of the panel features a specialized anti-reflective coating, keeping the surface dark so it can trap incoming light and force it down into the silicon layers beneath the glass. What happens inside that silicon relies on the photovoltaic effect, discovered in 1839 by French physicist Edmond Becquerel, seen here. His 19th century discovery remains the only mechanism we have capable of taking raw, static sunlight and turning it directly into usable electricity, all without a single moving part. To see how that works, we have to look closely at this animated diagram of a single solar cell. The internal architecture is essentially a silicon sandwich, split into two very distinct layers. The upper half is the N-type layer. During manufacturing, this silicon is treated or doped with phosphorus, which packs it with an excess of negatively charged particles called electrons. The bottom half is the P-type layer. This section is treated with boron, which does the exact opposite. It creates a deficit of electrons, leaving behind empty spaces, or positive charge carriers, known as holes. Where these two chemically opposite layers meet is called the p-n junction. Because of the extreme difference in charge, this boundary generates a permanent internal electric field. The entire structure acts like a tightly compressed spring. It actively holds all those negative and positive charges apart, waiting for an external trigger to set them in motion. That trigger arrives when a photon finally strikes the cell. The tiny light packet penetrates the silicon, violently colliding with an atom. The kinetic force of that impact knocks one of those trapped electrons completely loose from its bond, leaving a new, empty hole where it used to be. Because of the electric field sitting at the p-n junction, that free electron can't fall backward. The boundary acts as a one-way valve, immediately repelling the negative particle upward toward the surface. Multiply that by millions of photon strikes a second, and you get a massive crowd of free electrons gathering at the metal contact grid on top of the cell, where they are forced out into an external wire. That steady, uniform line of electrons flowing in a single direction is what we call direct current, or DC electricity. The panel has successfully turned solar radiation into electrical momentum. But this raw DC power faces a major roadblock right out of the gate. It is completely incompatible with the wiring of a modern house. Almost everything in your home and the broader electrical grid runs on alternating current, or AC power, and AC electrons behave in a completely different way than DC. To bridge that gap, the system relies on a crucial piece of translating hardware. Looking at this installation, you can see the solar inverter mounted on the wall right next to the home's electrical panel. This animation shows exactly what that inverter does. It takes the flat, straight flow of incoming DC electrons and mechanically forces them into a rapid, oscillating wave pattern, successfully generating AC power. Without that chaotic but carefully controlled conversion process, all the elegant microscopic physics happening on the roof would be completely useless to the appliances sitting in your kitchen. Once converted, that fresh AC power flows straight into the home's breaker box, actively running the lights, the television, and the refrigerator in real time. But during the middle of the day, under peak sunlight, a typical solar array usually generates far more energy than the house can actually consume. When that happens, the system pushes the excess electricity out of the house and back into the municipal grid. You can see the mechanism that tracks this outward flow here, an analog electric utility meter. This process is known as net metering. As that surplus power flows outward, it physically causes the dials on the electric meter to run backward, generating direct financial credits for the homeowner. Through this system, a residential house goes from being a passive consumer of energy at the end of a transmission line to an active, decentralized mini power plant. That excess energy travels up into these high-voltage transmission lines, flowing across the neighborhood to immediately power adjacent homes and local businesses. Over time, the localized impact scales significantly. It builds an electrical ecosystem that produces zero emissions, releases no pollution, and quietly sustains itself for decades. As we see from this wide aerial view of a massive commercial array, the scaling potential is vast. By mastering the microscopic physics of a single photon, we have built a mechanism capable of providing a clean, renewable foundation for the global grid.